Hello, today we are going to discuss quantum mechanics or quantum chemistry. Quantum chemistry or quantum mechanics is a very integral part of chemistry and it forms the basis for other important topics in chemistry like how bonding takes place between two different atoms or how electrons are arranged in an atom or a molecule. All these things are discussed in quantum mechanics. So to know quantum mechanics or quantum physics, we have to know about the history of quantum mechanics. From the ancient times only, we have known about the wave nature of light. We have known about the refraction, reflection, we have known about the interference and etc. All these phenomena actually establish the wave nature of light. Later in the 19th century, yes, Einstein discovered the photoelectric effect and Compton discovered the Compton effect. As a result of these two, we could establish the dual nature of light. The Compton effect and photoelectric effect actually established the particle nature of light. It was thought during the era of classical physics that light, which is an energy, has wave nature and all the matters have particle nature. So after that, Louis de Broglie thought that if light can have dual nature, then particle may also have dual nature, and he hypothesized that particles also have dual nature, and then he established an equation for the wavelength of a wave which is associated with the matter. He used these two equations, E is equals to h nu, which is Planck's equation, and E is equals to mc square, which is Einstein's relativity theory. Now equating these two equations, this is the wavelength for light, where c is the velocity of light, and for matter he suggested that lambda, wavelength of the wave associated with the matter, must be equals to h by mv, where mv is nothing but the momentum and v is the velocity of that matter. So it was just a hypothesis back then, and after a year or two experiments were performed which established the dual nature of electron or dual nature of matter. These two experiments were the Davison-Jarmar experiment and the Young's double slit experiment. The Davison-Jarmar experiment actually uses Bragg's equation or Bragg's law for electron, and in Young's double slit experiment there exists electron gun and a screen. Screen, and in between them there exists a barrier, and two slits are made in that barrier. This is the first slit, this is the second slit. Now there are only two possible ways for electron to reach this screen, either through this or through this slit, either through first slit or through the second slit, or through both the slit. So if the electron had only matter nature or the particle nature, then what would have happened is the intensity of electron in the screen would be maximum at this position and also at this position. The intensity of electron would have been maximum in this position and in the center where no slit is present corresponding in the corresponding region of barrier, we can say the intensity would be almost zero if the electron had only particle like property or particle nature. But actually it was found that electron the intensity pattern is something like this. Now you can see the maximum intensity is present at a position whose corresponding position in the barrier has no slit, but still intensity is maximum at this position. So if we can recall, we have read in our higher secondary days that when a ray of light passes through a slit, then we obtain in the screen a series of dark band, a series of bright band, again dark band, bright band, dark band, bright band. This we obtain, and this happens because of interference. A similar result is obtained. You see here it is highly intense, means intensity is high. Bright band. Here intensity is low. Dark band. Here intensity is high, bright band. Here intensity is low, dark band, and here intensity is high, again bright band. So we can say that the electrons have undergone interference after entering this portion, and as the electrons are undergoing interference, we can say that electrons have a wave nature associated with them. Now another thing is that if only one slit is present, then what will happen is that the intensity will be maximum at this position, and the intensity will be given as the function of square of the wave function at this position. If only this slit was present, then here the intensity would have been equals to the square of the wave function of this passage. Now here the intensity is actually the square of the wave function present here. So the wave function is psi1 plus psi2. Because of interference, constructive interference has taken place in here, and thus the wave function here can be represented as psi1 plus psi2, and their square will be equals to psi1 plus psi2 square plus 2 into psi1 psi2. This result is matched with what has been obtained from this experiment. Another important thing or fascinating thing is that you see we have obtained a pattern of intensity like this one. Right. Now consider that only one electron is ejected from this electron gun, which is propagating towards the screen. Now, as this electron reaches the periphery of this barrier, the electron is equally present near both the slit. That means the probability of finding electron near this single electron near this both the slit is same. That means this electron is simultaneously present near this slit as well as near this slit. This is an interesting observation. So now the dual nature of light as well as of matter is established. So now we will define matter wave. What is matter wave? Matter wave is nothing but just now we have studied that matters are also associated with a particular wave. The wave associated with the matter is known as matter wave. Now we will define another thing, which is wave function. What is wave function? Like the wave which is associated with a matter can be expressed or can be described in a space-time coordinate. Mathematically this wave, the matter wave, can be expressed or described in a space-time coordinate with the help of a function. That particular function which describes the matter wave in a space-time coordinate is known as wave function. Mathematical function which describes a matter wave in space-time coordinate is called wave function. And all the necessary information about that matter, like in energy of that matter, momentum of that matter, the position at which the matter is presently, all these things are incorporated in this function. Now let us consider something that there is a wall and a string is attached between the two opposing walls. Now if we create a disturbance, that means if we pull down the string and leave it, then what will happen? A disturbance will be created, and this disturbance will move. This disturbance that has been created will move towards the other end, and at the other end it will be reflected back by the wall, and it will move again towards this one, and again this one disturbance will be reflected back by this wall, and again this wall will reflect back the disturbance when it will reach that point. So there will be reflections of vibration and cross reflection and multiple reflection of vibrations. So this will lead to the presence of certain waves in the system. This will lead to the presence of certain waves in the system, that means in the string. Now you see, all these small waves can undergo constructive interference, and what will happen is that all these waves will vibrate together, and we can no longer see this individual small wave, rather we will see a bigger vibration of the whole string. The whole string will go up and it will again come down. It will go up and it will again come down, where this is our mean position. All the small waves that were present have undergone the constructive interference, and it appears that all of them are vibrating. You see, the amplitude is also greater in the final wave than the smaller waves. Here the amplitude is this much, and here the amplitude is this much. Only two positions, the two ends are not moving, but the whole string is going up and coming down. Now, there may be another case where this may happen. Few waves are directed in a particular direction, and others are directed in opposite direction. In this case, what will happen is that these waves which are directed in same direction will undergo constructive interference, and this wave will also undergo constructive interference as they are directed in the same direction. But at this position, what will happen? The two waves, or two newly formed waves, will meet, but the direction of these two waves are opposite. As a result of which, what will happen? This point, it would appear that this point is not moving at all, and this point will remain stationary. This point, which appears to be stationary, is known as a node. Similar thing will happen if this happens, then a constructive interference will take place between these three. Constructive interference will take place between these three, and constructive interference will take place between these three. Now you see, as the constructive interference has taken place here, in these 2 points, the waves of opposite direction are meeting, as a result of which destructive interference is taking place, and these are the points which appear to be stationary, and thus these waves are known as stationary waves or standing waves. This is a wave in one direction. There may be a wave in two directions or two dimensions, like a stretch, a sheet of rubber. Now, what will happen is that we have seen, if 1D wave is present, nodes are what? Zero dimensional. That means nodes are just a point. Now in this case what will happen is that you see this is the line which is same as the main position. That means the displacement from the main position of this line, this was the right, this was the portion described by dotted lines actually describe the main position. So this line in the center has zero displacement from the main position and thus can be considered as a node. But here you see the wave is two-dimensional. Here we have two dimension. For a two-dimensional wave, the node becomes a line. So if 2D wave, node is one dimension. And similarly, if 3D wave, like if you now make it a box, then what will happen? This will be like a box. Sorry, the drawing is not very proper or clear, but you can make an idea that the shaded plane is the plane which has not moved from the main position, and thus this plane can be considered as a node, and this is known as nodal plane. The node is two-dimensional. Oh, wait a second, let me check if it is recording or not. Yeah, it is recording. Now, let us come to Heisenberg uncertainty principle and understand it. Now you see, if we consider a very simple wave, a very harmonic wave where the wavelength is very much fixed, something like this. The wavelength is very much fixed. The wavelength here, or the wavelength here, or the wavelength here, or the wavelength here. The lambda is fixed, right? So, what will happen is that the amplitude here, 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 the amplitude is okay, it's equal. If here it is A, then here also it is A, then here also it is A, and so on. So if we consider a wave which is propagating from minus infinity to plus infinity with a very constant wavelength, then by de Broglie's hypothesis, wavelength can be given by this. If it is fixed, then momentum is fixed, right? If lambda is fixed, then momentum is fixed. But you see, as the A, that means the amplitudes are equal. Here also it is equal, and here also it is equal. That means the probability of finding the particle, or probability of finding the particle, is equal in that position, in this position, in this position, and this position. That means it will go till infinity. From minus infinity it will go to infinity. So that means the electron may be present anywhere between minus infinity to plus infinity. As we have precisely calculated or accurately calculated lambda, so the amplitude of the waves are same in all the positions, amplitude of the waves are same. So the probability of finding the particle or probability of finding the electron is same in every position from minus infinity to plus infinity. Thus, more is the precision in sorry, before that. Now, what if we compress this wave from minus infinity to plus infinity? We compress this wave to say minus a to a. Then something this like will form. Here you see the particle may be present anywhere. The particle may be present anywhere between minus a to plus a, but it is the region is smaller than minus infinity to plus infinity. We have compressed the wave. But here you see the wavelength is no longer static. Here the wavelength will not match the wavelength of this wave. It will not match with the wavelength of this wave. So, well, when we try to reduce the error in calculating the position of the particle, we have increased the error percentage or uncertainty percentage in wavelength calculation, and as a result consequently of momentum calculation. That means here del x is less. That means uncertainty in position is less, but del p is more. Here what happens is del p is less. That means uncertainty in momentum is very less, but del x is large. For this was explained by Heisenberg, and he produced an equation and produced a law actually, which states the momentum and the position of a particle cannot be calculated simultaneously. Or the momentum and the position of a particle cannot be measured simultaneously. And he produced this equation where the uncertainty in position and the uncertainty is momentum must be greater than or equal to h by 4 pi or h cross by 2. It can be described in another way as well. Let's see. Let us consider, sorry, the camera stopped working, so I will discuss it once again. Now let us consider that we want to see that electron. For that, what we need to do? We need to bombard this electron with light or photon. If we use a photon which has a very high wavelength or large wavelength, then what will happen is that as the wavelength is inversely proportional to momentum, as the wavelength is large, the momentum will be small, and thus when the electron and photon will collide, we know that after collision certain amount of momentum is exchanged. So after collision not much of momentum will get exchanged because the momentum is less. So here we can say that if you wanted to measure momentum, we could measure momentum more precisely. Therefore del p is small, or uncertainty in the calculation of momentum is small. But you see, if we use the wavelength of if we use wavelength which is much larger than that of the diameter of electron, then the electron may be present anywhere in the wavelength. So del x is more. Now let us take a photon which has a very small wavelength. In this case, you see, as the del x will in the earlier case the del x will be large. Okay, momentum will be small and del x will be large when the wavelength of the light is larger. But if we consider the wavelength of the light to be very small, then as the wavelength is small, momentum will be large because they are inversely proportional to one another, and as the momentum will be large, so after collision there is a bigger chance of gaining more momentum by this electron, and thus del P is large now. But you see this electron can be located more precisely by this wavelength. So del x is small. Thus we can say that momentum and position cannot be calculated precisely simultaneously or accurately simultaneously. And if we multiply the uncertainty in their calculation, then it must be greater than or equal to h by 4 pi. Not only in case of momentum and position, but also in case of energy and time, angular momentum and angle, we can say that these two properties cannot be calculated simultaneously. So the Heisenberg uncertainty principle actually states the accurate calculation or measurement of momentum and position cannot be done simultaneously. Now we will discuss a very important topic or a very fundamental topic in quantum mechanics or quantum chemistry, that is Schrödinger equation. You see, quantum theories have been given by many scientists actually, and to my knowledge by 3 scientists, namely Heisenberg, who used matrix mechanics for establishing his quantum theory. Then there comes Schrödinger, who used partial differential equations for his quantum theories, and then there comes Richard Feynman, who used actually the path integral method for quantum theory. Schrödinger and Heisenberg actually formulated in a same period. They actually formulated the theories of quantum mechanics in about same time, and after some time or after a year or so, it was shown by Schrödinger that both these theories are mathematically equivalent. A few years later, or some years later, it was Richard Feynman who established the path integral method. In chemistry, we largely use Schrödinger wave equation or Schrödinger wave equation for solving all our problems. It is a very fundamental problem and fundamental topic or fundamental law, fundamental equation, and thus cannot be derived. It is like F is equals to ma in classical mechanics. We cannot derive F is equals to ma. Similarly, the Schrodinger wave equation cannot be derived. But we can draw certain conclusion regarding the Schrodinger wave equation considering a classical wave. So let us consider a classical wave which is given by something like b square u by dx square equals to 1 by b square du square by dt square. Now you see this is well described in wave mechanics, and u is actually, now let us first of all consider a particle undergoing a wave equation or a simple harmonic motion. A particle undergoing simple harmonic motion. So if this position is u, that is, it is the main position, this is the main position, this line is my main position. So the displacement from main position is u. What is it? What is u? It is displacement from main position. It is actually a function of space and time. What is v? V is the velocity of the particle. Okay, it is actually here, u is actually the dependent variable and x and t are independent variables. So from our elementary mathematics we know that if a function is represented this way, if a function is represented this way, then we can separate the variables to this, where this x is only dependent upon small x squared and capital T is only dependent upon t. Also from wave mechanics we know u can be given as psi cos omega t. This is also derived from wave mechanics, where u is the displacement from the main position, psi is the maximum displacement or amplitude, psi is maximum displacement or amplitude, and omega we all know is 2 pi nu, where nu is the frequency. So if we put this equation in this equation, then we will find that let us carry out the mathematics. After performing this mathematics, we can conclude that we will get this equation, where the cos omega t will be cancelled, and we will get this equation that implies Now you see we have written omega as 2 pi mu, so omega square will be 4 pi square mu square, and v is actually given as mu lambda, so mu square lambda square, mu square lambda square. 4 pi square by lambda square psi. We have obtained this equation. Now from de Broglie's hypothesis we will put the value for lambda. How we can do that? Now let us consider the total energy is equal to the sum of kinetic energy plus potential energy. That means kinetic energy is the difference between total energy and potential energy. We know kinetic energy is half mv square, and this is equals to P is actually now equals to twice m e minus u and root over whole thing. So this is our momentum, and from de Broglie's hypothesis we know lambda is equals to h by p, that implies p is equal to h by lambda. No, we can put the direct. Oh no, we need to do that. H by lambda. So now we will put the expression for lambda in here. I don't think, yeah, I'll do it here. Lambda square is nothing but h by p, right? Sorry. H square by p square, it will be since p square remains in the denominator, so it will move in the numerator. Here you see in this equation we have put this value of lambda. In this equation we have put the value of lambda from here and p from this equation, and we have come to this equation. So this equation becomes this is the basic Schrodinger wave equation, where psi is the wave function which is only dependent upon space and not time. We are not discussing the time dependence Schrodinger wave equation, but we are here just discussing about the time independent Schrodinger wave equation, and this is how it looks like. This equation can again be rearranged as a square by 8 pi square m square by psi square plus u psi equals to E psi. Now you see there is a double differentiation operating on a function. To give back this function, this function multiplied with certain constant. Here, so this is an operator which operates on a function to give back that function multiplied with a constant. Operator, function, and this is constant, and this is again the same function. So this function is known eigenfunction, and this constant is called eigenvalue. So now, as we have discussed earlier, that a wave function actually contains all the necessary information about a wave. So any physical property or the knowledge about any physical property or quantity can be gained from that wave function. How will we gain that? This is the way we'll operate that function with an operator which would result into that function multiplied by a constant, and the constant will be a particular physical quantity, and this operator actually will be very specific for specific physical quantity. Like for momentum, if we operate this wave function with a momentum operator, then the physical quantity, then the constant that we will obtain after this operation will be the quantity of the momentum of that system. So this equation is known as eigenvalue equation. This equation is called eigenvalue equation. Now you see, let us consider there is a wall, there is another wall, and we are actually considering a 1D space, and an electron is enclosed between two walls. In the very beginning of the lecture, we have come to know that chi square means intensity. Now what is intensity actually? Now if we say that we have seen certain graphs like this where it is wavelength and here it is intensity. We say that the intensity is maximum for the wavelength, say 400 nanometer. What does it mean? It means that the total number of photons obtained, the maximum number of photon is of wavelength 400 nanometer. That means out of the lot, if you pick up a photon randomly, then the probability of finding a photon with 400 nanometer is maximum. So intensity can be related to probability, and thus chi square also gives probability. If you can remember that in the double slit experiment that I have explained, an electron when reaches the periphery of this uh, what is called barrier, then the probability of finding an electron in front of slit 1 and the probability of finding an electron in front of slit 2, they both are same or equal. So the intensity and probability are related, and thus probability is also given by chi square. So what is the probability of finding an electron? Since this electron is enclosed by two walls from the region 0 to A gas, minus infinity to plus infinity. So what is the probability of finding that particular particle in between 0 to minus infinity? It is actually 0 because the particle is enclosed by wall. And again, what the probability of finding that particle from A to plus infinity is 0 because it is confined by this wall. But what is the probability of finding that particle? In between this, it is chi square is equals to 1. Because as the electron is enclosed by two walls, then it will have to remain in between that this space, this one-dimensional space. Therefore, chi square is always 1 for this particular area or this particular region. Now, if we consider a very small space element like say dx, now what is the probability of finding an electron in this position? Actually, Schrodinger considered that the wave function is uniform throughout the region. That means if the electron is enclosed from here to here, there are no barriers, no nothing, so the wave function will be uniform in this region, and thus the probability of finding a particle in this space element will be chi square into dx, the total probability plus probability of finding this particle in here, in this small space element. This is known as probability density. Why density? Because the probability per unit area. What is the probability of finding an electron in that area? That means the probability per unit area or per unit space. Therefore, it is known as probability density. And this is probability. What does it mean? Quantum mechanics is actually probabilistic in nature. We cannot certainly say that the electron will have to be present here or there. No, we cannot say that. But it only deals in probability. In some places the probability is more, in some places probability is less. This formula actually of integrating chi square dot dx from 0 to a was given by Born, Max Born. This formula was given by Max Born. Now we have gathered a lot of information regarding the wave function, the Schrodinger wave equation, the probabilistic nature of quantum mechanics, the Heisenberg uncertainty principle, dual nature, etc. And now we will discuss what are the criteria that the wave function or a function should follow to be considered as a wave function. Number one, it should be continuous. Number two, it must continuous slope. It must have a continuous slope. Number three is finite. At any point it must be finite. And number four, actually single valued. So these are the four criteria which a function must follow if it has to be called a wave function. The first one is the continuous wave function. The wave function must be continuous. If it is so, the function is like this, that means the function is not continuous, or it is like this. Okay. So the function is not continuous, you see. So at the position A, there is a sudden change in the slope of this wave function. Thus any physical quantity we are going to measure will show an abrupt change as it reaches point A. This will destabilize the system, and thus any discontinuous wave cannot be considered as a wave function. Second one is the wave function must have a continuous slope. Here you see the wave function has a continuous slope till x equals to a. But as soon as it reaches the wave x equals to a, there is a large increase, or there is a sudden change or infinite change in slope at x equals to a. The slope was like this, but as soon as we reach a in x, as soon as we reach x in this position, there is a sudden or a large change or an infinite change in the slope, and thus the discontinuity in slope or discontinuity in slope cannot also be considered as a criteria for wave function. So the wave function must also have a continuous slope. Third is the wave function must be finite. Now let us consider this one. The wave function is not finite. Like at x equals to 0, it is infinite. Or let us consider another example. That means at x equals to a, somewhere it is meeting at infinity. So now if we want to normalize this wave function, then we will see something like this. Now what is normalization? Normalization is nothing but here it is from 0 to infinity, right? So if you want to see the wave in a window of 0 to 1, then how will it appear? This is known as the normalization. Since it is in infinity, so it will appear at 1 and others will be in 0. Other points will be in 0. So you see, this type of wave after normalization actually violates the first two criteria, and thus this is also not considered. So a wave function has to be finite if it has to be considered as a wave function. Next is single valued. Now you see there are A, B and C. In C, the wave function is single valued, but in B you see, in A you see, the wave function is not single valued at A and B. It means that there are multiple probabilities or multiple solutions. If you want to calculate the probability of finding an electron in this position or this position, then it will have a multiple probability, and it does not make any sense. So the wave function has to be single valued. So today we have learned about some basic concepts in quantum mechanics, and we have learned what are the criteria a wave function must follow so as to be called as a wave function. And in the next lecture we will learn about the quantum mechanical postulates and operators. Thank you.